Welcome back to Plan and Manage Schedule. In the first part of this lesson, you saw the overall task, its enabler workflow, and the proactive mindset that drives good scheduling. Now it's time to get into the mechanics of estimating. In this part, you will learn how predictive projects define the work to be estimated, and then you will work through the two core predictive estimating techniques, parametric estimating and bottom-up estimating. You will see the exact formula each one uses, walk through two full worked examples with real numbers, and understand the genuine trade-off between speed and accuracy that determines which technique you reach for on a real project. Before you can estimate anything, you need to know what you're estimating. Predictive and adaptive projects define that work in two very different ways. In a predictive project, you define activities using the work breakdown structure, or WBS. It decomposes total project scope into deliverables, then work packages, then the activities you will estimate. This gives you a complete, fixed inventory of the work before estimating begins. In an adaptive project, there is no fixed WBS. You define work through the product backlog, an ordered list of stories and features that the product owner continuously refines. Unlike a WBS, the backlog is expected to evolve as the team learns. This distinction matters because it determines what comes next. Once predictive work is decomposed down to activities in the WBS, you're ready to estimate each one using parametric or bottom-up estimating, the two techniques covered in depth ahead. Once your activities are defined, predictive projects turn to one of two math-based techniques. The first is parametric estimating. This technique uses a statistical relationship between historical data and some other measurable variable, square footage on a construction job, lines of code on a software project, or meters of cable on an installation project. The formula is simple on its face. Estimate equals quantity times unit rate. But the real skill is in the unit rate itself. It has to come from solid historical data, not a guess. If your team has reliably installed cable, poured concrete, or written code at a known rate before, parametric estimating turns that history into a fast, defensible number for the new project. Get the rate wrong, and the whole estimate is wrong just as confidently. You need to install network cabling for a new office floor. Your team's historical data shows they install 10 meters of cable every hour. The general formula is estimate equals quantity times unit rate. Here, your quantity is the total scope of work, and your unit rate is the historical productivity your team has already demonstrated on similar cabling jobs. Because this unit rate is expressed as a speed 10 meters per hour, you convert it into a duration by dividing the total quantity by that rate, rather than multiplying, since you are solving for time, not distance. 1,500 meters divided by 10 meters per hour gives you 150. That is your duration estimate, expressed in hours of work. The blueprint calls for 1,500 meters of cable, and your team historically installs 10 meters every hour. Divide the two, and you get 150 hours. A fast, data-driven duration estimate built entirely from historical performance, not guesswork. The second predictive technique is bottom-up estimating. Where parametric estimating applies a single historical rate at a high level, bottom-up estimating goes the opposite direction. You decompose the work down to its smallest possible components in the work breakdown structure, estimate each one individually, and then add them all together to get your total. Because every piece gets close examination, bottom-up estimating is widely considered the most accurate technique available to a predictive project. The trade-off is time. Decomposing every deliverable down to granular tasks and estimating each one takes far more effort than plugging a number into a parametric formula. You will typically reserve bottom-up estimating for activities where precision matters most, or where you simply lack a reliable historical rate to lean on. You need to estimate a user login feature. You break it into its smallest tasks and estimate each one on its own. First, you estimate each lower-level task on its own. Designing the database schema takes 4 hours. Building the API endpoint takes 8. Building the front-end interface takes 12, and writing unit tests takes 6 hours. With every component estimated individually, you simply add them together. 4 plus 8 plus 12 plus 6. That addition gives you 30 hours total for the entire login module, a bottom-up total built from real, granular estimates rather than one broad historical rate. 4 hours of database design, 8 for the API, 12 for the front end, and 6 for testing add up to 30 hours. That is your bottom-up estimate, slower to build than a parametric number, but grounded in a detailed look at every piece of the work. So how do you choose between these two techniques? It comes down to a genuine trade-off, not a simple either-or rule. Parametric estimating is fast because it leans on one historical rate, but that speed only produces an accurate number if the new work genuinely resembles the historical data behind the rate. Feed it mismatched history, and it will confidently produce a bad estimate. Bottom-up estimating is the most accurate technique available, because every component gets individual scrutiny. But that accuracy costs time. Decomposing and estimating dozens of small tasks takes far longer than a single multiplication or division. In practice, project managers often use parametric estimating for a quick rough order of magnitude early on, then apply bottom-up estimating later for the activities where getting the number right truly matters most. Start with any predictive activity that needs a duration estimate before it can be sequenced and scheduled. Ask yourself the deciding question. Do you have reliable historical unit rates for this exact type of work? If the answer is yes, use parametric estimating. Multiply or divide the quantity by that trusted historical rate to get a fast, defensible number. If the answer is no, or the activity is unusually risky or unfamiliar, use bottom-up estimating instead. Decompose it into its smallest components and sum the individual estimates. Whichever path you take, treat the result as a starting point. Recheck it once real work begins, since actuals often reveal that the rate or the decomposition needs adjusting. That covers the two core predictive estimating techniques. Parametric estimating gives you speed by applying a trusted historical rate, quantity times unit rate, as you saw with the network cabling example reaching 150 hours. Bottom-up estimating gives you accuracy by decomposing work down to its smallest pieces and summing them, as you saw with the login module reaching 30 hours. Remember the trade-off. Choose parametric when you have solid historical rates and need speed, and choose bottom-up when precision matters most, or that history simply is not there. In the next part, you will see how adaptive projects size their work using story points and relative sizing. That's it for this lesson. See you in the next lesson.